So let's start slowly. Good morning, everybody. So after 1 week, we meet again in this team room. Okay, somebody have already sent me the example. It's good way. Okay, at the end of this course, I will repeat again because some students ask how to share these example and so on. Nobody ask about the problem of the static, but maybe it is a new thing. So, okay, once again, on the screen you see that you see my surely my name, telephone number, and room where I am sitting normally. Okay, so you can contact me not only during this lecture, but also later. Even if you have some problem with not only with the static and dynamic, but with anything, maybe something with work at our university. So contact me. Okay, you have telephone number and mail, and also normally it is better to send me via email because if I have time, so I can answer it. The team chat room it is good only for the lecture because I can contact you directly. Don't send me the question via the team after lecture, okay? Because I have another duty, so it is better if you send me message and question and something, even the exercises to the email, okay? To the email, it is better for me because on my free time, beside of other duties, I can ask to answer to you, okay? So we repeat again that in this picture I will show you many times, not only today, but in later in second course in the second semester. You see that the mechanics deal with the relationship between force and motion. However, in this first course, in the first semester, we are dealing only with the force because the the system of rigid body in the equilibrium. Okay, it means that we have the system. Sorry, we have the system with we have the system of many rigid body which are in the equilibrium. It means that they don't move, or maybe sometimes they move with the whole inertia coordinate system with the constant velocity. So in this case, because we don't say anything about the motion, so we are dealing only with the equilibrium, okay, of the body. It means that we study or we are interested with everything concerning the foxes, or sometimes we call it the fox system theory. Fox system theory. It is the first course, static, and the second course we will dealing with the dynamic. Okay, and it's split into two parts: kinematic. In kinematic, we will deal only with the motion, and in the most general portion, we have a kinetic. It means that we study the relationship between motion of rigid body or mass point or particle also, and the forces which are have already investigated in the last time, and this code is the force. Okay, so yeah, uh, we will repeat this many times. So in this first semester, we have only static again, and your task we are dealing with the forces. Okay, so we have already said that the first time in the first thing for anything that we are dealing with this chapter, so-called Fox system. Okay, Fox system. Fox system theory. It means that we are interested in anything concerning of foxes. Okay, again, I repeat it last time that fox system. What is a fox system? A fox system is a system of many foxes which are acting on only one body. Okay, later, so the assumptions that all foxes acting on one body is very important. It creates a basis for everything. And after that, we can extend this fox system to the system of many rigid body. However, in this case, we step by step, we should assume, or we should take into consideration any other assumption. Okay, so at first moment, remember well that we are speaking about fox system. It means that we assume that all foxes acting on one rigid body, absolutely rigid body. Okay, no deformation. So in this chapter, yearly or later, we define fox vector. And one two thing very important for important thing is the for characteristic for fox vector is a resultant fox. Any fox system can be reduces to two things: resultant fox and resultant couple. Last week, we have already investigated resultant fox, any fox system, and today we will start with the second very important characteristic of the second property of the fox system is beside of resultant fox, we have resultant couple or resultant moment. Okay, resultant moment you see here, resultant moment. And with these two things, resultant fox and resultant moment, we can reduce any complicated fox system to these two things. And after that, with reduction of or reduced fox system, we can consider if the system is in equilibrium or in the motion. Okay, remember well. So why we study last time resultant fox, and today we'll start with the second characteristic. It means resultant moment. And what is this? What is it? um, Last time we started with the resultant fox. Okay, resultant fox. But at this time, because we didn't define the moment and resultant moment. So last time we are dealing only, we we specify only resultant fox of several concurrent foxes. Okay, concurrent foxes. It means that the foxes, all foxes passing through one common point. Okay, it means the concurrent foxes. You see here. If if I have a fox system which consists of F1, F2, and Fn. And in Cartesian coordinate system, because I use a fox vector, I can use a component in X, in Y, and in Z, in X, in Y, and in Z component. And from this, I can calculate resultant fox by adding all foxes, or you take the sum of all foxes. Okay, we have two methods for calculate the resultant fox. The first method is a drawing method, geometrical. It means that step by step I can use a parallelogram for two foxes, F1, F2, and we have the one smaller result. And after that, I adding the third one, and step by step I can add it. Okay, so it means, and I apply parallelogram step by step with two foxes. And it is better if I can, beside drawing directly the parallelogram, it is better to draw so-called polygon. It means I will take one point, fixed point A here, and I will draw parallel line. For example, at first time, I draw F1, F1 here. I bring F1 from the original position to this one, parallel. And at the end of this vector, I draw parallel line with the F2. Okay, it means that I bring F2 to this position, from original position to this position. So you see that if I have, I will draw parallelogram, so I will have one fox here. And after that, I draw diagonal of this parallelogram. And after that, I will bring F3 here. And I draw the diagonal of the parallelogram again. So in this case, you see that step by step, if I bring all foxes from original position at the end of the with the continuing the polygon, so the line or the vector closing this polygon is a resultant fox. You can prove it very easily by applying parallelogram step by step. Do you understand? So you see, you can prove very easily. So if you have the good geometrical tool, okay, so you can using this drawing method. But for computer, it is better the second method, using the projection method, algebraic. It means that I calculate all the three components of each foxes, like here. Okay, fx, fy, fz, and I will provide summarizing of each component in x component, in y component, and in z component. And after that, you can calculate the magnitude of the resultant fox easily by Pythagorean theorem. Okay, by Pythagorean theorem, I calculate it very easily, and with all these three components, I can calculate very easily also the direction. Uh, with the unit vector. Unit vector, remember well, unit vector show the direction of the resultant fox, like Fi here, but the magnitude of the unit vector all the time is 1. So here you see, if I have the total vector and I have the magnitude of vector, so I can calculate very easily the unit vector of direction. Or you can find also cosine alpha, cosine beta, cosine gamma with FRH, FRY, and FRZ. Okay, it is only repeating what you have already done last week. Okay, and again, I emphasize that why you are doing it. The first thing we have already investigated, resultant fox, and today we will you will do with the second characteristic for the fox system. It is so-called resultant moment. With these two things, we can reduce any complicated fox system. Later, not today, but next time we'll see that any fox system can be reduced with these two vector, resultant fox, resultant moment, and with these two things, we can see that this system either in equilibrium or in the motion. Surely, in this semester, we can take only the case where the system is in equilibrium. The rest is for next course, next semester. Okay, so again, today we will do with the resultant moment. So first thing we do, that we will define for calculating resultant moment, we should define a moment. And the special case of the Fock system is a coupler also. So we will define the moment of a Fox. Very important. Remember well. I repeat it. Moment of what? Moment of a Fox. Above what? Two things. And sometimes it leads to the error or misunderstanding of the student or also of the engineer. Remember well that I want to calculate moment of a fox. Above what? Above a point or above an axis, above a point or above an axis. Okay, and later you see that this moment can give the rigid body the tendency to rotating. So why we are speaking about movement of a force above point or above an axis? It means that this moment give the body a tendency to rotate above one point or above an axis. Okay. And after that, after defining the moment of a force above a point or axis, we will define resultant moment. Okay, and after that, we define something special case, moment of a coupler. What is coupler? Maybe you know it from the high school, even from the physics. It is quite easy. However, today we will see an overview of everything. Okay, so first thing, moment of a fork above a point. You see here, I draw some dot. It is meant. It is the second part. We will dealing with the moment of a force above an axis, but it is later. At this moment, you will define the moment of one force. This force has a point of application at A, okay, and the magnitude and anything with the direction. It's described by this vector, okay, this red vector. And now I take a point O, and I want to calculate the moment of a force F above point O. Normally, I can denote it by MO, like a scalar. You can define it by using algebraic or scalar analysis. Or the second way, you can define it by using vector analysis. You can define moment like a vector. But at first, you can define it like a one scalar. Usually that if I have one force with line with direction, it means I have a line and one point, so I can construct one plane. Okay, so you see here it is plane of your paper or your screen, or I have, because I have one line, one point. From geometry, you know that if one line and one point on the time, you can construct one plane. So this plane in this case is this plane of this screen or this paper. So first thing, everything I will define in this plane. So in this plane, I can measure the distance from this line, of this line from this point. Okay, so D. And the moment of the force F above point O, denoted by M O, is defined by this one. MO equal F times D. It can be take the sign plus or minus. The plus is a counterclockwise and minus is clockwise. So you see here again, if the force acting in this direction, so really it keep the moment or the tendency. If I have some rigid body lying on this plane, you see really this rigid body has the tendency to rotate above point O in this direction. So it means that it is a counterclockwise, so it is a positive in the positive direction, so I have a sign plus. So here, if the force F have the direction in opposite direction, really the tendency of the rigid body will in this direction. Okay, in this direction. So we can see that really in this case I take the sign minus. Remember well, later you see if I define a vector of moment, so you see that you can use right hand rule, but at this moment, because anything I can define it in this plane, so the moment is a positive if it is a counterclockwise. Okay, counterclockwise. Again, if the structure of the rigid body is clockwise, so it is negative. And now, one note, one remark for you. Any foxes I have if I have another fox F apostrophe has the same magnitude and the direction as F and is equivalent if have the same line of action, and therefore they produce the same moment. Okay, so you can have the another fox which is equivalent and it has the same line of action and should give the same moment. Okay, later you see that the if the vector of the moment, you can see that the result of the this moment should be the same if I have the same moment of the fox. Okay, and now what I have already said in the last slide or the previous slide, you have already specified the moment like a scalar, and now better for us for later using in the dynamic, and also it is better to define the moment of a fox above point like as a vector. It means that I should use vector to describe this moment like a fox. A fox, last week you see that a fox can be defined by one vector, and the same for the moment. You see that if I have a fox F, red car here, I have a point O here, okay, and I want to calculate the moment of a fox F above this point O, okay, and some minutes before I construct the plane containing fox F and point O, and in this plane I measure distance D and I calculate F time D. And now I doing something. I will do something. I specify a position vector OA, where A is a point of application of fox F. Or later you see that I can use any point of which is lying on the line of application of F. And here we can say that A is the point of application of F. And I specify position vector from O toward A. So I have a vector OA. I have a vector OA like a vector R. And you see that I can calculate very easily that this moment can be calculated by using scalar definition F time R sin theta. Theta is a measure from the positive direction of vector R or OA, vector R, OA, to the positive direction of F. So you see angle theta here. And in this case, it gives sine theta. It gives really this one, FD. And this is the magnitude. It is the same like in scalar. And the direction of this moment, I can use the so-called right-hand rule. Right-hand rule, again, I repeat it. If I rotate positive direction of R to positive direction of F, so the thumb will show the direction of the moment. Okay, you see here. This picture again specify or explain it later in the next slide. So you can write it. This moment is cross product of vector R time F. But at this moment, look at this picture to remember well the direction of the moment by using the right hand rule. You see here again. If I have vector R, vector R here, OA, okay, on the left side, it's too slow, okay, and vector F here. Some students have the mistake, the error, but surely you see here again, for finding the positive direction, so I should postpone or I should extend this vector R in this direction, and from this I can measure angular theta, and from this sine theta I have, you see again that I have angular distance d, f time r sin theta, and angle theta with this direction from vector r to vector f, the thumb will show the moment, the direction of the moment m. Okay, so you see here, repeating anything, I have the Fox f with the three component fx, fy, fz. I have point of application 8 somewhere, okay, 8 here, with the, and I want to calculate the moment of this force above point O. So I have 3. In this case, with many discussion some minutes before, I can write MO like cross product R time F. Okay, R time F. And you see that with the convenience of the mathematical operation, cross product with the Cartesian coordinate system, I, J, and K. So I use a determinant. Okay, in this case, MO can be calculating very easily by using computer or something like, for example, if you MATLAB or Mapper, or also so calculate very easily. But you can calculate it yourself if you know the component of F and R. Surely this vector has the magnitude exactly like some minutes before when I calculate with F time D like here, okay, or FR sine theta, or you can use a mathematical way to calculate it, okay. So at this moment, remember well, direction of the moment of force F above a point, it can be calculated. It is perpendicular to the plane constructing or consisting of F and O. The direction is specified by using right hand rule, and the magnitude can be calculated by using either F time D, this one, okay, F time D, okay, this distance, or using cross product R time F, using determinant and so on, okay. That remember, maybe somebody, for somebody it is quite easy, for somebody because it is require a lot of mathematics. So okay. And now after some um, some theory, and today, for because it is really morning, next time we start exactly at 6:45, and maybe we have a quiz exactly at the beginning of the lecture. And today it is a bit later, after half of hour. And how many students are here? Oh, 40. It means that 10 students is missing. And now we will quiz. And all of you will try to do the quiz and write the answer. Write the answer on the chat room. Okay. Okay. I will give you 5 minutes. So first question. I have a Fox F. Okay. Fox F here. Can be applied in the 2D program, in the configuration here for F. For example, in this configuration, in this direction, in this direction, and in this direction. Okay. Q is a perpendicular. R is a lesser than 90 degree. R is a better, and S is in this slide. So for these four cases, P, Q, R, S for these cases of the position of fox F. Select the case resulting of the maximum and minimum moment. Okay, the moment. Okay, in very many, Mr. Wing. Wait, here is the second question. Write directly to again, Mr. Minh here and write it again. Both. If you write, for example, AB and AC and okay, repeat the question because I have already. Write directly. For example, you write 1A 2C or 1C 2B. Oh, good. Okay. Write okay. Answer. Okay, good. Some problem with the computer too slow. So you see again that I don't know if the COVID situation will longer or not. So if you will, if if we have the examination in online, so something like this should be in the quiz. Okay. 5 minutes for this quiz. It's quite easy today. It is only for starting. You see that you understand well the definition of moment of the fork of F. You can use either for the first question. You can see that the correct answer is a correct answer. Many students correct answer is surely 1D 28. Why? It gets quite easy, okay? Because you see that if you can calculate the distance, or if you use a scala on the scala, okay, scala definition, so you can use very easily that the maximum should be position Q, okay, and the second one S is passing through this point, so should be 0. So the correct answer is QS. The same for the second question. If you define M times R times F cross product, so you see surely M should be perpendicular to the plane which are constructing with the from the R times F. It means that M is perpendicular to vector position vector R. So because this is perpendicular, so if I provide a dot product, so surely that the correct answer is 0. Okay, right. So it is only for refreshment from the instead of breakfast. So we have the quiz. Okay, quite easy for you. So after quizzes, and now we will have the real problem. You have the moment. You should calculate the moment of a force F with the magnitude 100 Newton. Direction is specified in this way. In many textbook, in English textbook, you write something like this. It means that they don't give you, normally in Vietnamese textbook, they give you, for example, angle alpha here. But in English speaking country, normally they give you this way of calculating 3, 4, 5. From this, you can calculate the angle with the vertical or horizontal or vertical direction. Okay, so try to find the moment of the force at point 8. Okay, 5 minutes for you. It's quite easy. However, step by step, you go to the. You should be very familiar with these things. Good. Đừng đến hiệu trường Giang. Okay. Wait, we will see. Wait for other people. Mr. Nguyễn Thanh Bình. Okay. You see, Mr. Trần Văn Minh Hiếu, another result. There are many things in the physics or example that almost all students at the classroom have the same wrong result. Only one few students have the good result. You will see. You can use either scalar analysis. It means that you can calculate the distance of Fox F, or you can use a vector. Wait a bit for anybody to finish it. How many students have already? Only 1, 2, 3, 4, 5, 6. 7. Not good. Only 10%. Oh, 10%. 50% student can finish this example. I don't say if it is correct or not. However, remember, well, all the times your activity on the classroom, on the course, will be represented in the final midterm. Okay. You see, somebody has almost student have the same. I don't know if the wrong or correct. Somebody have another different. Pay attention that if you have the online examination or the test, the correct result, numerical result is very important, because the machine will specify only the correct answer if you have at least four significant digit. Okay, in this case, not you have three significant, it is okay, because but if you have more, pay attention. I don't know if you have rounding off error or not. Okay, you have a many way to do it. One way is using scalar analysis. It means that you can calculate the distance of the Fox F from point out. Okay. However, it is not so easy. It is better to use a vector calculation, vector analysis. It means that I will resolve the Fox F along x and y component, and after that, with x and y component, I calculated the distance very easily. Okay, so here I express the Fox F into component fx and fy. So you see, because I use a trigonometry, I calculate fx and fy very easy. And if fx and fy, I can calculate the distance of fx and fy very easily. It is 5 and 2 meters. So from this, I calculate it very easily with 460 Newton meter. Nobody write the direction of this moment. So even you have 460 Newton meter, but nobody surely, if you have the some assessment here, so it means that you don't have total or complete complete or 100% correct answer, because you should specify also the direction of it means that it should be minus, counterclockwise, clockwise, sorry, clockwise. Surely that in this case you see that the beam has the tendency to rotate above this point in this direction, counterclockwise, sorry, clockwise. It means that it is minus. Okay, so you see that. I check it again. If somebody has the correct answer, nobody is a side. Somebody has the uh, magnitude incorrect. Okay, so you see, it is very important for you. Okay, I have the program with the keyboard. Second. Okay, the first example quite easy, but you see that even it is easy, but you don't have a 100% correct answer. This one next, more complicated. This one a 3D problem. In this case, it is very, very, very important that you should use a vector analysis. Okay, again, repeat the calculation. The force and geometry show as a picture. Try to find moment of F above point. Oh, submitted. This one is more complicated, not from the mechanics point of view, but from geometry. But you see that even from the first one, either it is very easy, but nobody gives the correct answer. Surely in this case, we cannot use for 3D program. It is too complicated to use scalar definition. Okay, you cannot calculate the distance. So in this case, you should use a vector analysis. So specify or try to describe force F and position vector A and C. It is a connect some point here, and we want to calculate the moment using vector. Right here for the last time. step by step. Here are some results for you. Fx, Fy, and Fz. And also position vector. Mr. Nguyễn Hữu Trường Giang again, fast and furious. So in this case, this is for 3D program. You see that you have already side. Last side is too simple, so nobody knows about the side. And here with using the vector analysis, because in 3D, so you see that you have the sign. Surely, if the two vector, I use a cross product. Only Mr. Nguyễn Hữu Trường Giang has a result. Now here's the result. Okay, for any for the for all of us to see. Okay, two things I would like to remark to note. One thing that if again here I have a determinant. Okay, determinant. It means that it requires the mathematical operation for the people who cannot understand well the problem. So check it and discuss the problem with you. Okay, it is basis knowledge of the mathematics. So you see again, I have a vector here, I, j, and k. One thing. Here, for example, if you look at this result and the result of Mr. Nguyễn Hữu Trường Giang some minutes before, pay attention that at the quizzes or the test or the examination online, normally because it is created by machine, so all the side you should specify using how many significant digit. Mr. Zhang here uses, for example, 4 significant digit. Okay, but here at the result I use only 3, so it depends. Normally for engineer it is good way that I have 3 or 4. If in the result it is required that you should have 3 significant digit, it means that in the intermediate calculation you should say 4 significant. Okay, here it is only the final result I have 3 significant digit. Okay, Okay, anything? I think this is clear. And now we will go to the it is better if somebody, for example, you calculate also the magnitude of this with the Pythagorean theorem. Right? You three component x, y, and z. You calculate the magnitude and angular also. Okay, cosine angular. But it is enough because in the example is given, it is required only to calculate the moment f above point O, okay, over point A. And now we go to the second part of this moment of we have okay, Mr. Hill, why do we have to use a cross product for 3D instead of dot product? Okay, Mr. Hill, why you use dot product? It is from the definition. Moment of a force above moment of a shock above a point should be defined by cross product. Those product it does not given anything. It is not definition. Definition of moment of a force above a point should be defined by using cross product. Those product is another thing. Those product is a cross product or those product or other product. It is only tool. Is a tool, mathematical tool for defining something. You can use it either in physics, in mechanics, in even in, I don't know, somewhere in astronomy or somewhere. But for mechanics, for defining the moment of force F above a point, the definition is a MO is cross product of position vector F. Okay, it is not dot product. Why dot product? Dot product is another thing. You can use the scalar calculation, but it is not product. Okay, it is only one way to calculate it by using algebraic construction. But definition is this one, R time F. It is a so-called vector analysis, and this one is a algebraic analysis. The first one, F time D. Two way to calculate the moment of a force above a point. Algebraic or scalar definition, and after that, even after that, you should define a definition. If I use, for example, a scalar definition here and use a right hand rule, so you see that the positive direction will show to me, to us, and negative is towards the paper. Okay, and both definitions should give the same result, and this one is a cross product. Mr. Hoàng Đình Lượng give the piece of apply to Mr. Hiếu. Okay, but it is you should discuss in English because you are in advanced course. Okay, it is not Vietnamese. Okay, I cannot understand well the problem in Vietnamese. Mr. Hoàng Đình, okay, I see Mr. Hoàng Đình. Okay, what is this? Hoàng Đình Lượng. Hoàng Đình, I check in the print. Hoàng Đình, where? Hoàng Đình Lương, Hoàng Đình Lương An, sorry, Hoàng Đình Lương An, okay. Good. Okay, we have already shown it. Mr. Hoàng Đình Lương An shows the picture. So again, I show this picture again. You have this one, okay. Good, but don't be upset if you have any problem. So ask me, okay? Ask. And after the lecture, you can ask the friend also, okay? Oh, and now we will go to the next more important things. Moment of a force beside of moment of a shock above a point, and now I will define moment of a force above an axis. How we can define it? Again, pay attention. I see that many mistake, confusion, like some minutes before you ask if you can understand where's the problem here. Here, it is the picture. You see that I have the pipe, an axis here, and now I have a fox. You see that the tendency and the behavior of of this um, uh, this rigid body will be in any way if I act the fox in this direction, or in this direction, or in this direction. The tendency of rotation of this rigid body above this axis, it is quite different in these three way of the fox. Okay, so in this case, I should calculate, or I should specify the moment of a fox F above this axis Z. Okay, so what is this? The first one, again, here is on the above picture, or the first these are three picture, you have the real case. But here in the mathematics, okay, please switch off your microphone. Who is this? Okay, switch off microphone. Anybody? Okay, this is better. Don't forget to switch off your. Okay, so, and here on this picture on the right side, in the corner, I try to describe the situation. I have axis delta, and now I have fox F, and I can calculate the moment of this fox F above this delta, axis delta. There are many ways to do it. One way is I explode this fox in two components. First component F2 is parallel to delta. Second component is parallel with the plane perpendicular to the axis delta. So you see that F2 don't give any contribution to the tendency of the rotating of the rigid body for delta. So F2 have no moment, only F1. So here I can use last definition. If I project F in the plane perpendicular to axis delta, and calculate the F moment of F1 to the point O. Point O is the intersection point of the plane, okay, of F1 perpendicular to delta. So in this case, you see that in this construction, I can calculate the moment of F above delta. It means to give the rigid body the tendency above to rotating F delta. However, it is too complicated. So you see that the first definition is the moment of fox F above the axis delta, the M delta, can be defined as the moment of this component F1 above point O. Okay, it is quite logical. It means that I project fox F to the plane F is a F, it is a perpendicular to the axis delta, and O is a intersection or intersection point of axis delta and the plane P. And after that, I calculate I use the scalar definition to calculate it. Okay, so you see again here, Mr. Okay, it is not dot product. It is only scalar. Okay, not product. It means the product of two vector. Mr. Okay, some minutes before I show it again. Mr. Trần Văn Minh Hiếu, even we write F1 type D here, but it is not dot product because here F1 and D are scalar. Okay, it is not product. Dot product is the product of two vector. Maybe you are confused with the cross product and dot product. Okay, even we write here dot, but it is only scalar or algebraic analysis to calculate the moment. So it is the first way to calculate the moment of force F above an axis. Okay, so like F1 is like this one. This is the first case. If I have the force which are in the perpendicular plane and give the rigid body the tendency to rotate, oh, it's quite easy. Okay, and surely if this Fz here, like here, you don't have any tendency to rotate above z axis. You have tendency to rotate above another axis, h axis. Okay, and this one give no moment. Here again, I repeat it: scalar analysis. Scalar analysis. I use the moment above force F, the moment above y-axis here, y-axis here. I can, because it is perpendicular to this plane, so it is quite easy. All the time, check the perpendicular to the plane. Okay, construct the plane perpendicular to the axis, and after that we can calculate it. Okay. However, you see here that it is not sometimes, it is not can be found very quickly, dh. It is better in this case to move like to the vector analysis, because not all the time, like in the previous cases, I can calculate the arm dx quickly if I want to calculate my dx here. Okay, so in this case, it is better to use vector analysis. Vector analysis here. Again, I have a axis. In this case, it is axis AA, axis A axis, and I have a force head here. Very general. And again, I draw position vector of 1 point on the line of application of F, and which point O, and I construct it R times F. And now, what we will do? First thing, I use a cross product again to calculate the moment of F about any arbitrary point O on the A-axis using cross product. This one we have done some minutes before. Okay, if on the line on the axis 8, I use some point O, and this point I define a position vector. I calculate MO by using cross product R times F. This is quite easy. No, it's quite easy. You can understand well. Okay, so it means that I construct the perpendicular plane. Okay, I can use determinant. So you see here it is MO. MO, it means the moment of force F above this point O. And after that, I can use, I project this moment MO to the project it MO to MA. And only in this case, I have one vector. Second vector is a unit vector, UA. Only in this case, I project it, and I use a so-called dot product, like Mr. He asked some minutes before. It is the product of two vectors. First vector is the moment of force F above point O. I have one vector. And I have a second vector describing the direction of this line, A, UA. So in this case, I use a dot product to have the moment of force F above axis A. So in this case, you see, I use a mathematical operation. First thing, cross product for calculating the moment of force F above this point. And after that, using those product to project this vector, to this one. And surely, because I use those product, this one MA in this time is a what? Is a scalar. Okay, it's a scalar. However, in this picture, you see that I draw this this vector again. I can define it like a vector because here I have magnitude. Okay, those products give us one scalar. It is magnitude of this vector, and the vector I have unit vector axis, so I can define this moment of the vector above axis like a vector with the magnitude UA times MO, the product, and the direction of UA. Okay, do we understand? Pay attention. Pay attention. I will explain it more in detail, but pay attention that only in English textbook, normally you can define it as a vector. In Vietnamese textbook, because I see that many students read as a reference some textbook in Vietnam language. Okay, in the course in Vietnamese or in Vietnam, normally they or we define moment of force above an axis like a scalar, no vector. No vector. Pay attention to this. I have a remark for you. Only in Europe or in American, they define it one thing more. Besides of magnitude, I give the magnitude of the unit vector, so I have a vector. Okay. So step by step again. I have a moment of a force above this axis delta. Again, I have a force F, and now I have two steps. First step, I fix some point O on this axis delta. Okay, axis delta. And I first step, I calculate the moment of force F above this point O by using cross product. You see here, cross product. I can use either matrix representation or using geometric representation, vector representation of one vector. Okay, cross product. So you see here, using cross product, I have a moment of force F above this point O. Here it is a vector, and here's a tendency of rotating. And now the second step, I project this moment to this delta axis. Okay, you see again, I have first line, I use this dot product. It is the dot product. So I have the scalar because it is scalar. Dot product, you can use the position. The first term or second term, it is not so important. You can use either UA here or UA here. So you see that here, the definition in Vietnamese textbook finish. It means that all the time the definition of the moment of a force above an axis is a scalar. However, oh, you see here again, I have a mathematical definition determinant. Here it is cross product. We have done some minutes before, and I provide a dot product with a position vector. So I get, you see again, if I have three components, 1, 2, 3, 1, 2, 3, 1, 2, 3. So really after that, I have only magnitude, only one numerical arrow. No, sorry, number. Like one numerical value. So you see again that the moment of the force F about axis Z is 0 if F is a parallel or intersects delta. As some minutes before we have seen in this picture. Okay, this picture. If this one is a parallel to Z, so don't give any moment above Z. They give moment only above Z x-axis. Above Z-axis it is 0. This one also, if F here intersects Z-axis, so it gives a 0 moment. Okay. Is only okay. So here it is a node, and I have already said to you, I can define moment of F about axis passing through as a scalar, like in Vietnamese textbook, and it finish here. However, you can define it as a vector. If I take this scalar and using unit vector in line delta, so I have a vector also. In English textbook, they use also this one, this definition, and this so-called triple product. After that, they use cross product, those product, and after that they use one unit vector more. You can see here. This one is a triple product give a scalar 1 minute, one only magnitude, and after that I couple it with the unit vector u delta. So in this case, I have a vector m delta. Okay, so it is a note for you. You have a discussion with some friend or even you have some tutor in Vietnam. So pay attention to this. Maybe they don't understand what you will speak about, because all the time in Vietnamese textbook they say that the moment of F is about axis delta is only scalar. Okay. Okay, so we have example. So it is better to see at this, so we can do it after break. Okay, for some students, so go break, and after break you can do it. Or do you think that it's better to do now? It is break is better. No answer. Okay, 10-minute break.
I think we can do it now.
You can do it now.
Yeah. So
okay, so
free break.
After finishing, so we take a break. So do it. I give you some minute to make an orientation. So we'll do together. Plan. Mx, in this case, you see that you will define it as a triple product, cross product, and after dot product to project it into X. Okay, specify a point O here. So I have a position vector from O and A, and after that find a specify unit vector U in X axis, and after that to calculate the arm type M. Okay. Here it is the plan for you. Mr. Nguyễn Hữu Trường Giang again. Oh, we'll see. But we wait a bit for other people. Good, Mr. Phan Tung Sơn again. Mr. Doan Nhật Minh, good. I don't know if it is correct or not, because just now we have again noted the number of significant digit. Okay, with the Mr. Sun, for example, it has 4 significant digit. Mr. Đoàn Nhật Minh also, but Mr. Phạm Văn Lộc, it is take too many significant digits. We see. Minus. Why minus? Okay, so unit vector for defining about axis x is unit vector I. Okay, but now we will define specify the vector for force F and position vector ROA. After specifying these two vectors from the geometry, you can view triple product. First, cross product, and after that, dot product. With the triple product, you can use a determinant. Okay, you can use a determinant. So you see, here's the result, cross product. So somebody remember before to look at the textbook from the mathematics also. Okay, so here's really I have a 17.4 with a 3-digit significant digit. What is a CCY? It is a counterclockwise. It means that it is really it is counterclockwise, because the positive direction of x is this direction. So counterclockwise, it means that it is a positive one. Okay, y, counterclockwise. So after finishing, here it is for some people who cannot catch the. You can take you can see during the break. So we take a break, 10-minute break. Okay. 10 minutes. Okay. So let's continue, okay? Oh, Mr. Hyo, vaccination. I don't know. If it's at home, you can continue it. Okay. Okay. Anybody?
Yes, teacher. I continue.
Oh, yeah, let's continue. Okay. We continue with the second one example more. Okay. This one. Maybe the the same like before. There are many students have the good results. It is good preparation for the uh, next portion. Okay. Again, I have Fox F. With this case, we have angle alpha beta gamma, and try to specify the moment of Fox F above this axis to give this pipe of the bracket um, to rotate about this AA axis. Again, the situation or the strategy, the same like some minutes before. We should specify the unit vector for AA, okay, unit vector of this axis A, and position vector ROA, and also specify the component, Cartesian component of Fox F, and using triple product again. So some minute after refreshment from the break. Step by step. First thing, two unit vector. Oh, two unit vector, one unit vector and one vector position vector. AA is a parallel to the y-axis, so it has the direction of axis y. Mr. Video Trường Giang again has for 5 minutes after finishing. We are waiting for other people. Good. Mr. Nyan, the same result, however, with the opposite direction. both the same magnitude. The same magnitude. I see that many students have the same magnitude. Only, I don't know if it is correct or not, but you can see that many students have, they have the different sign. Okay, it is clockwise or counterclockwise. Here it is F. Again, Mr. Buhay. Again, he use a triple product. Okay, the first thing it is a triple product. With the first row is a unit vector, the second row is a position vector, the third row is a vector of force F. And after that, you can define very easily the magnitude of force moment F. But you see that as a result, because I don't know what it is a calculation, it is positive. It means that you again see here, it is counterclockwise. If I see from the if you see from the positive direction of the unit vector UA. So you see here on the picture, it's a magenta color. It's a magenta color, the direction of the rotation. You see that moment really gives the bracket the tendency of rotation counterclockwise. It is because it is positive. It is positive. So check it, Mr. For example, Mr. Bùi Hải Anh, Mr. Nguyễn Thanh Bình, check it. Why you have the sign minus? Why you have the sign minus? Check at home, okay? It is good that everything, it is good that you have the magnitude. However, if on the online checking by machine, if you have the not correct sign, it is zero. So check it. Why you have the sign minus all the time? Okay. So we have finished this example. Two examples are quite from the point of view of the mechanic. You see again in this definition. You see the definition of moment of the force above a point, and after that, moment of a force above an axis. It means that normally I calculate the moment of a force above a point, any point on the line, and after that I project it on the line to get the moment of force above an axis. And this one is only preparation for further step. First thing, resultant moment, and after that leads to the reduction of force system. So as we have already discussed some minute before, beside resultant force of for any force system here, F1, F2, F3, and Fm, just now we want to specify resultant moment of a force system, because and why we do it and what is necessary, what is useful for, you will see later for reduction. But here, imagine that I have a force F1, F2, F3, any, and just now I fix some point O, and I want to specify the total moment of all forces above this point. So this one is the definition of resultant moment of a force system. Resultant moment of a system of forces or force system is the summation of all moment of all forces above this point. So we see again, Mr. Cannot remember, okay, it is cross product again. And I calculated the moment of a force above one point. I have cross product in this definition. And each force have a position vector of force, and I calculated the moment of each force above this point O and provide a summation. Okay, and it is a definition. And here it is a one Varignon theorem. In any textbook they give this Varignon theorem, but I don't think that it is so important. However, okay, I take F instead of it's good. Okay, again, because we are speaking about resultant moment of system, I the arrow with the sign of minus. Again, you see that for cross product it is very important the position of these two vector, which one is the first, which one is the second. So you see in the chat room, Mr. Nguyễn Thái Minh found himself the mistake because he write F time R. It is the cross product. For dot product, the position of the two vector, it is not so important. However, for cross product, it is important. Okay, because for example, you show you the right hand rule, so you see that the positive direction from the first one to the positive direction of the second one, and the thumb will show the positive the result. So you see that first one and second one, if you change the position, so surely the result the result is incorrect. Okay, Mr. Bing, good. It is important that you can find your it is not important at this moment that you have an incorrect at the example incorrect result. It is not so important, but important that you know where and why I have this mistake. Next time you don't have it, because one forever after, and just now you remember well that it is should be R time F like here, not F type R. Okay, it is a definition. Oh, good. And now come back again to Varignon theorem. Again, it is like here. The moment of a force above a point is equal to the sum of the moment of the forces component above the point. It looks like a result. The in this Varignon and theorem, and we say moment of a force above a point. It means this force really it is a resultant force. Later you see it. So at this moment you can see that this force can be exploded to the many components. And Varignon theorem say that the moment of all components above the point, it is the same like a resultant moment. Okay. of resultant moment. So at this, remember well, this Varignon theorem might be because the proof you can prove it. However, it is not so important. Important is remember well this one, because next in the derivation. So sometimes we call point to the Varignon theorem, so you know what is this. It means I have a fox, I have the component. So it means that the moment of all component above this point, it is the same like the moment of this fox, okay, like the resultant fox later with some point. Okay, like here. If I have a F1 and F2, so you see I have resultant moment, a resultant fox. If I calculate the moment of this, so you see that this fox can be replaced by one diagonal by parallelogram, or you can see that resultant fox, and after that you can calculate very easily by using this. Yeah, you see MO, it is moment of two foxes, moment of F1, moment of F2 above point O, and after providing this, so it is really F1 plus F2 give us a resultant fox. So at this moment, you see that something is connecting or some relationship with the resultant fox, a resultant moment. Okay. And now we will go to the so-called moment of a coupler. What is a coupler? It is a special cases. If you don't like it, you can say that I have a fox system which consists of two fox, F and minus F. However, it is a special case. Special cases. So it is better sometimes if I have two foxes have the same magnitude, they are parallel, and in the direction is the opposite. So in this case, I can create so-called coupler, the coupler. Okay. And what about this for this one? In this case, you can see later, or you can guess like an engineer. After this, important for this coupler is the moment of this. Maybe the magnitude of which component for this is not so important. Two couplers should be the same, give the same behavior if they should have the same moment. Maybe the fox is for example, greater, bigger. But in this case, the distance between them should be shorter, and they should give the same coupler. How we can define it? You can write here. If I have a fox, and now I calculate the moment of this fox above any point. For example, for this point, for point O, using the definition, of moment of a fox above 1 point. So I have a fox moment of a fox F above point A. Okay, and sorry, above point O, but the point of application is a point A here. Okay, and now I calculate the moment of the second fox minus F with the point of application point B. You see here, and after calculating, so R time F, it is the same, so I can have A minus B, so it is a vector from A to B. So it is the result is very nice, because you see at this line that moment of this coupler is only magnitude F time vector R. It is two arbitrary point of on the line of application. And if I use a scalar calculation, so R times sine theta, so F times D. So you see that really the magnitude, the moment of coupler, what I have already said some minutes before, is only the product of magnitude F time distance between these two forces. So you see it is a very nice thing that it is coupled. It does not depend directly to the magnitude of the force F. Either F can be smaller or bigger, but the coupler should be the same if I have the distance bigger or shorter. Okay, M times FD. So take for example, if you take the wheel driver volant in your the car, you see that the driver can take with the bigger distance of two hands to keep and to rotate the volant or the wheel on the car with the big force or small force. It depends if by the distance of these two forces. Okay, so in this case, like some minutes before, here it is a definition of by scalar. However, I can use it like one vector because the magnitude is F times D. So in this case, I can construct the plane. In this plane, I have both forces, F and minus F, and the vector will be perpendicular to this plane. Okay, this plane, and the magnitude should be F times D. So in this case, I have a vector moment of a coupler. Pay attention that it is a free vector because it can be applied. I can move this vector anywhere, and the behavior and or uh, application of this vector can be in anywhere, and the effect of this coupler should be unchanged. So in this case, moment a coupler will have can be represented by one moment. Direction is perpendicular to the plane containing two forces, and magnitude is F to D. Direction is either upward or the rightward by using right hand rule, but you can see very easily that in this case I have these two forces, so tendency of rotation quite easily if I use a right hand rule. If it rotates in this direction, so the direction of the moment is upward. Okay, so it is important that moment of a coupler it can define. So you see again that using this vector, I can see what I have already said some minutes before. Two couplers are equivalent, or it means that it is the same, or it gives the same effect if FD1 times FD2 and they are parallel and have the same effect. Okay, and all the time they have the same tendency to cause the rotation in the same direction. You see again here in the second picture, if I have D1 and D2, even the direction of the force are not the same, the magnitude also. However, if I have F times D the same, so in this case, the effect of rotation at the rigid body should be the same. Okay, so I call it these coupler are equivalent. Okay, and which is vector again with the advantage of the mathematics, I can do many things. I can use addition. I can calculate the resultant vector as form of the coupler. Okay, you see here Varignon theorem, also M1, and also resultant coupler for many forces which create each two forces a coupler. So I can calculate the resultant coupler for many coupler. Okay, so here it is only some summation of advantage, mathematical advantage. If you want to use the mathematical for mathematical operation for calculating. Okay. Okay. Again, it is repeated by vector many ways. You see here for your understanding. Here I have a coupler. The first picture, two forces in distance d. In this case, I can create one coupler. one coupler. Which coupler is perpendicular to the plane. You see the plane here, consisting of by two foxes. So the plane, and the plane is what is perpendicular to this plane. Magnitude is F times D, F times D. Okay, and if you have the vector, so I can see the rotation, the tendency of the rotation by using, for example, right hand rule. Okay, and now because it is the free vector, so I can move the origin here, from here to origin. It is quite maybe for somebody it is surprising, but it is no surprising. It is quite normal that it is a free vector, the same magnitude, the same direction. So in this case, it is not like a free vector, Fox vector. It is a coupler. So I can move this vector of coupler from this point to this point. Quite easy. Okay, it is one very nice thing, and later you will see that you will use this magnitude property many times. Next, maybe separating again. No, I have a vector. So because I have a vector in coordinate system x, y, and z, so I can explode it into three component, mx, my, and mz. So really, it is a very nice thing that from the first picture, I can explode it into three component in x, y, and z here. First thing, calculating the vector moment of a coupler. After that, moving it on the origin of a coordinate system, and after that, explode it into three component. Okay, nice things. Okay, again, see, read at this thing at home, and feel the nice thing of the mechanics. Okay, coupler vector are free vector and can be resolved, can be exploded into three component, mx, my, and mz. Okay, nice thing. And now it is one example. Look, at first it is very simple, but not it is so simple. If you, like engineer, you see at this, so maybe you see that it is not so easy at home. And so you see that here it is really you are working with a rigid body, not like a point, okay, for mass point. So I have a two coupler. Two coupler. It means that each coupler created by two forces. The first coupler is the F and minus F. Okay. The second one is a 2 kilonewton and minus 2 kilonewton. Okay, so kilonewton here, and this one give us in this problem I have already I give you 2 kilonewton, and here I have F and minus F. So one your task just now is specify magnitude of F. If the resultant coupler moment is 1.5 kilonewton meter clockwise. Okay, clockwise. Again, it is very important that with the coupler, I don't say that above what, above which point, because it is a free vector. It is a free vector. So feel that the nice or the sense of this example and the sense of the topic of the coupler. Okay, do it. I give you some minutes for making orientations, and after that you will do together again. So here it is a plan. Somebody have already the result, but maybe the result varied. They are different. So we will see. So we will see it. Okay. After finding the resultant couple, have time D, because here we have the 2D problem. So it means that the vector presentation is not so necessary. It is only simplify your calculation. Only simplify your calculation. So in this case, I can find very easy the resultant couple by using scalar approach. Okay. And after that, because I have F here, so after that I have 1.5 kilonewton, and after that I can find Mr. Lương, what is the N T thầy? I cannot understand well the Vietnamese. So okay, N T, what is this? NT. You see that many students think that normally, because you are in Vietnam, I see that many students use, for example, I think that you have the problem with I was talking to Nhân, and it is a nice try thầy. What is this? And T is a nice try. Nice try. 2 times. Thầy. What is this? If you go, for example, because you are with something before, if you are going to America or to Europe, in Vietnam all the time you say thưa thầy, thưa thầy, thưa thầy, but just among the younger people, okay, but okay, don't mix in Vietnamese. And normally, if you go to Europe or to American, don't say teacher. You should say professor or something like this. So, but because I understand well, but I don't know in English course they don't say to you because they call, for example, Professor Phong. Don't say teacher, teacher, because in Vietnamese all the time you say thưa thầy, but in Europe in English right away you should say sir or professor. Don't say teacher. Okay, so I see it. Okay, only one. Not funny, but it is. I give you some advice if you go to Europe or to have some contact with the other professor from university. Don't say teacher, say professor or sir. Okay, yes sir, yes sir. So dear professor, not dear teacher. Okay, I see that it is a problem of English. Okay. Again, you see here, you see that we have 2D problems. So it is quite easy to calculate the coupler, moment of the coupler using scalar analysis. Scalar analysis, okay? And pay attention to sign, plus or minus, counterclockwise or clockwise. So if you have a 3D program, it's too complicated. So, but all the time, use a right-hand rule that will give you. So in this case, I get the moment, the total moment, resultant coupler of this. And because the required that I calculate for clockwise, okay, clockwise, so it means that it is negative clockwise here. So by equating both sides, so we really solving this for the unknown for f, we get f equal 2.33. Okay, good. At this moment, again, I emphasize pay attention because I take many examples from videos, but you see all the time, it is important. Just now, I repeat it again, that for online tests or quiz, it is important. All of the example today, you see that we have 3 significant digit, okay, 3 significant digit. I saw that many students have already, for example, Mr. Phan Tung Sơn, last result have 4. Okay, so pay attention to this. At this moment, it's not so important because I don't require you to give to give you how many digit and significant digit. Okay. Okay. Let's move further. What is it good for? Next time you will pay to very, very important thing. But what we have done today and the last week, anything is a preparation for this result. Any complicated Fox system can be reduced in 2 things: resultant Fox and resultant coupler. Okay, I have already said at the beginning today. And after finishing this lecture, you see that you are already able to calculate first thing resultant Fox from the previous lecture. And today you are able to calculate also the resultant gap or resultant moment. Okay, you see here resultant Fox is a summation of all forces. Okay, a resultant moment is a resultant moment of all forces above 1 point and above point O plus the all coupler. All coupler have already done. C here stand for coupler. O here stand for moment of forces above point O. Okay, MO. Okay, so here you see that next time you will prove it. So you see that any complicated force system can be reduced to only two things. You see, for example, here I have force F1, F2, F3, and any force and any coupler M1, M2, and many things. So after that, I fix some point O here. I move all forces. I calculate all forces to this point. So I have a force F1, F2, F3 in which way I will see next time. And the coupler is a free vector, so I move it here also. So you see at this second picture, here I have two systems. One system of concurrent forces. And you see that concurrent forces can be replaced by only one forces you have seen last time. And coupler also, all coupler I replace it by one coupler. So you see really at the last picture, the origin force system by many forces and many coupler have been already converted or reduced in only two things, FR and resultant force and MRO, resultant coupler. And with these two things, you will discuss if the rigid body is in equilibrium or it will move. So you see here, for example, I will have 4 cases. Think about this at home, like a homework, and maybe if you go with your girlfriend, you can discuss with them. With these two things, a force and one coupler. So you see, I have many cases. The first case is equilibrium. It is the case of the first semester equilibrium. Okay, nothing changes. This one is 0. This one is 0. It means that nothing acts on this rigid body. Surely this body is in equilibrium. The rest might be this one is 0. So I have only one force. Or the second one, the force is 0. Only the coupler. So it is a one coupler system. Or it is a screw, like when if a screw and we rotate it. So these are 3 cases give the rigid body the tendency to move. Okay, only the first one is okay. So it is a sense of why we have two two lecture last week, and this week how we do it leads to the so-called reduction of a force system, and this give us the sense for studying the equilibrium of rigid body or not. Next time we do it, or maybe you will read it at home to understand where the problem beside of doing homework. Okay. So homework again, we explain it some minutes. First thing, read textbook. What I have already said. The topic from the previous week, this lecture also, and maybe it is a good thing that you read some page more about the reduction of a force system in the textbook. Okay, I have already posted. And also solve the problem on the small textbook. Some students have already sent me, and it is if you have time, it is good. Many students have already sent. For example, 14 example is good. Somebody asked it is necessary to do 14 or not. It is good if you do 14, but it might be, it depends on your time. If you have enough time, you do it. You play with this. Okay, do it. And I don't say anything that you should, but if you have time and it is it is good for you to understand well, enjoy the problem, so do it. Not even today's topic, but pay attention to this. Somebody remember when I have already said this time. When you send me, please send me to my email address. Don't send to the team or to the for example one driver. It take me. I don't have so much time. Okay, please compress your all your problem and send only one file. This morning, early morning, I see that some student has me send me 5 or 6 picture. It take me time to register it. Okay, send me only one file. And in this email, in this file, please specify your name, class, because we have 2 classes. Because we don't have any other student with the same name, so it is better. Don't write your ID. It is enough if you write your name, your class, 61 or okay, 20, okay, 128 361, okay, and the number of problem 2.1, 2.2, or from 2.1 to 2.15. It is better, save it save me time, okay, giving me more easier to work. Okay, do you understand? Only one file, email, compressed, don't give me many picture. And in this picture, to make a quick orientation, your name, class, and number of program. Okay, so IT, do you understand well? Any question?
No, sir. We understand.
Good.
Sir.
Any question? So I write. If no, so see you again.
Goodbye, Professor.
Bye bye. See you again.
See you later.
Don't go good. I'm not teacher. Okay. See you again. You learn English also. It's okay.
Goodbye.
Goodbye, teacher. Goodbye, professor. Sorry.
Okay,
Goodbye, sir.
good.
Goodbye, teacher.
Okay. Okay. So I show you my. If you want to see my. Okay, here you are. So why somebody know me? Stop recording.